Alright, let's get started with our limits and continuity unit test under the course Calculus. What do we have for the first question? Find the limit as x approaches negative infinity. So we can't plug in negative infinity here, so we need a form that would help us plug in or substitute, direct substitution for negative infinity. And in order to do so, what we can do is we can divide this term, the numerator, with x cubed. The greatest order of x is 3. So we divide it with x cubed so that nothing remains in the numerator, and if anything remains, that is in the denominator. In order to balance this out, we can divide the denominator with square root of x to the power 6, such that when x to the power 6 gets multiplied with half, that is square root x cubed. Now, because we have negative infinity, like x cubed equals negative root of x to the power 6, because this is for negative infinity. If this was for positive infinity, then yeah, x cubed would have been equal to positive root x to the power 6. So that's why we need a minus here. Now if you divide this with x cubed, we get 5, x cubed can cancel out, negative 3 by x squared. And here we can take out the root as common like this, and we can divide 4x to the power 6 with x to the power 6, negative 7 by x to the power 6. So, and negative is here, so we have negative root 4 minus 7 by x to the power 6. Now we can plug in negative infinity. So if you plug in negative infinity, this entire thing becomes 0, because when you divide a fraction with a very large number, it effectively becomes 0, and so this also becomes 0. So if it becomes 0, above we only have 5, and here we have 5 by root 4 is 2, negative 2. So it's negative 5 by 2. Negative 5 by 2. There we go. Next question. Which of the following functions are continuous at x equals to negative 3? Let's plug in x equals to negative 3 here. What do we get? Negative 3, negative 3, negative 6 cubed. Positive number, we get a value. But what about this? If you plug in negative 3 here, it's 0. 1 upon 0, we don't get a value. So this is not continuous, only g is continuous. 1 upon 0 is undefined. So that's why we didn't get that value. Find the limit of this function as x tends to 3. So if you plug in 3 here, 3 to the 6 minus 5 is 1. Negative 4 divided by 1 is negative 4. So negative 4. Okay. We want to find limit of this function as x tends to 0. Direct substitution and other algebraic methods don't seem to work. Looking at the graph fx equals to x by sine x, we can estimate that the limit is equal to 1. To prove that the limit of this function as x tends to 0 is equal to 1, we can use the Squeeze Theorem. Haley suggested that we use the function g equals to e to the power x and hx equals to e to the power negative x in order to apply the Squeeze Theorem. Does Haley's suggestion seem to be correct? No. Why? Because Haley's suggestion is correct because it's not true that the output of the function is always below fx and the output of the other function is always above it for x near 0. As you can see, this graph, orange one, is above fx for x is greater than 0, below fx for x is less than 0. And this graph h behaves the same. It doesn't stay constant. It is above for some portion and below for some portion. So this is not true for this specific reason. Okay. Function g and h are graphed. Okay. Find the limit of gx minus hx as x tends to 0. This is basically saying to find the limit of gx as x tends to 0 and then subtract it from the limit of hx as x tends to 0. So what do we get for gh as x tends to 0? We get a limit of -1. So -1, we have -1 minus hx. This is hx. What happens when x tends to 0? Is 0. So minus 0, we have -1. Next question. Function h is graphed. Select all correct statements about h at x equals to -2. So x equals to -2 here. What happens? Both limit of hx as x tends to -2 from positive side and negative side exists. So if we approach it from the positive side, we have a limit which is -infinity. And for the negative side, we have a limit which is +infinity. Yeah, this is true. They exist. But the limit doesn't exist because they are not equal. They exist, but they are not equal. One is -infinity and one is +infinity. And h is defined at x equals to -2? No, h is not defined. We don't get a value when we, when we plug in x equals to -2 in this equation. So this is not true. And it is continuous. If it is not defined, how can it be continuous? So this is not true. Only a is true, and obviously none of the above cannot happen because a is true. Oh, the limit is so infinity. They don't count infinity as a limit. So limit is a finite number, so both of them approaches infinity. So infinity can't be a limit. A limit is like, as the word suggests, it's it's something finite, the maximum limit that we can get as you go on and approach a particular value. So here the function approaches infinity. So infinity is not a value. So if it was something like a finite value, like let's say -2 or +2, in that case, yeah, this statement would have been true. But because they approach infinity, this is not true. So now we understand that E is the answer. Okay. These are the graphs of the function f and g. Dashed line represent asymptotes which function are continuous of the interval -3 to 1. So -3 to +1. Yeah, it's continuous. -3, no, it's not continuous because we have an asymptote here. So A is the answer. Okay. Function f is defined over the real numbers. This table gives several values of f. This is a table appropriate for approximating the limit of fx as x tends to -5. If not, why? Where is -5? Right there. Is it approaching from both sides? Yes, it is. Is the interval equal? No, it's not. Is it getting closer to -5? Yes, it is. From both sides? Yes, it is. So yes, the table is appropriate. table A is appropriate. In fact, the limit is -2, as you can see. From both sides, we approach -2. Okay, consider graphs A, B, and C. The dashed lines represent asymptotes which graph agree with the segment. Okay, we want the limit of fx as x tends to 2 to be -2. So we infinity, my bad. So we are approaching 2 from both sides to get -infinity. This is true. But what about this? We get -infinity here, but we get +infinity here when we get to 2. So this is not true. And this is the same thing. So this is not also true. We only have A. Okay. Let h be a continuous function on the closed interval 0 to 4, where hx, h0 is 2 and h4 is -2. Okay. So 0 and 4. For 0, we have 2. Let's say this value. And for 4, we have -2. This is this value. Now, which of the following is guaranteed with the intermediate value theorem? So at least, if it is continuous, you would get the y values for any of these between 2 and -2, between 0 and 4. So hc, some value equals to 3. Basically, 3 is above 2. For at least 1, 2, -2 and 2, no. It's not true, because 3 is above 2. And you will have, as you can see, like, how is this? You're going from 0 to 4, it's getting downwards. How would it go approach upwards? Yeah, it can, but it's not guaranteed. And what about -1? -1 is in the interval. For at least 1 c between 0 and 2, this is true. And 3, again, it's above 2, so it's not true. Again, it's -1, but for at least 1 c between -2 and 2, no. We are going beyond the interval 0 to 4. -2 is far left. So only B is the correct answer. Okay. The function g is defined over the real numbers. This table gives a value, a few values of g. What is the reasonable estimate for this function as x tends to -8? Where is -8? Here is -8. It is approaching from the left and the right. And as you can see, it is approaching a value of 0, most likely. Or no, between -0.02 and 0.01. So it's 0 actually, yeah. Okay, function g and h are graphed. We have to find the limit of this hx times gx as x tends to 3. So that is the same as finding the limit of hx as x tends to 3 and multiplying that with the limit of gx as x tends to 3. So hx as x tends to 3, the limit doesn't exist because the limit of hx as x tends to 3 from positive side equals 5. The limit of x equals to 3 from negative side is 1. So the limit of h's doesn't exist, but that doesn't stop us to attempt a different, using a different method. So for gx as x tends to 3 from positive side, and the limit of x tends as x tends to 3 from the negative side. Okay, so from positive side we have a value of 1, and from negative side we have a value of 5. Then if you consider only the positive side, let's say positive, so 5 times 1 is 5, and the negative side, -1 into here 5 times 5 is also 5. So the sum for all positive is 5, and the sum for all negative is -5. They're equal. So we can say then, okay, the limit exists and it is 5. There we go. What is the limit of sine x as x tends to pi by 3? Okay, so x tends to pi by 3 for sine x. We have sine x. And we want to find as x tends to pi by 3. Okay, so it's something in this range 0.866. So let's see, and what do we get for this value? It's the same thing, as you can see. So B is our answer. Okay. This is the graph of the function h. Select all x values at which h has a removable discontinuity. As you can see, we have a removable discontinuity here and here. So 3 and 6. X equals to 3 and 6. What about x equals to 0? No, we don't have a removable discontinuity. It's a sharp turn. And as you can see, removable discontinuity and removable discontinuity. Okay. Find the limit of this function as x tends to 4. So if you plug in 4 here, we get 9. So root 3 minus root 9 is 3. And 3 minus 3 is 0. What about this? 4 minus 4 is 0. So indeterminate form. We have to change it. We have to change it with by multiplying it with the conjugate. So we multiply it with 3 positive root x plus 5, and in order to balance this and cancel this out, preserve equivalence, we multiply the same thing. Then a plus b times a minus b is basically a square minus b square. So 3 square minus, when you square this, the square root disappears and we only left with this thing. Now 3 square is 9. 3 square is 9. And this thing is going to be multiplied with this thing. And we have multiplied with this conjugate. A plus b minus b, a square minus b square. 3 square is 9. Plus 5 is 14. So x plus 14. What about this? X plus 14 doesn't cancel out x minus 4. A square minus b squared. This is not correct. A plus a minus b, a plus b. A square minus b squared, a square minus b squared. So 3 square 9 minus b square, which is x plus 5. We had the root, we squared it out, it got cancelled out. So 3 squared is 9. 9 minus x minus 5. So 9 minus 5 is 4 actually. So we are left with minus x plus 4. And if we take minus common here, we get x minus 4. Now we can cross this out with this thing. But we have a minus. So the minus, basically on the numerator, we have 3 plus root x plus 5 because of this minus. And now we plug in 4 here. So it's 9, root 9 is 3, negative 3 plus 3, negative 6. Okay. The table gives selected values of the continuous function g. Can we use the intermediate value theorem to say that the equation gx equals to 5 has a solution where negative 20, between negative 20 and negative 18? Well, let's plot this out. Negative 20, negative 20, negative 18, negative 20, negative 18, Negative 16, negative 14. Negative 16, negative 14. These are the values of the x. And for y, 10, negative 20, 30, negative 40. Okay, 10, negative 20, 30, negative 40, 20, negative 18, negative 16, negative 14. What are the values? 4 values we have. There we go. What has they asked? Gx equals to 5. So we need y equals to 5. Where are those? Where it is between. It is between this value and this value. So between the interval negative 20 to negative 18, can we say the solution? Okay, so negative 20 and negative 18. So 10 to negative 20. Can we say that at least we have one value? Yes, because it must cross. If it is continuous, it must cross this line in order to go from here to here. So negative 20 to negative 18, from 10 to negative 20, it must cross 5. Yes, both conditions for using the intermediate theorem have been met. No, since 5 is not between. No, 5 is between. Since we don't know if the function is continuous on the derivative, we know the function is continuous. So let's see. Okay. Function f and h are graphed. We have to find the limit. First, we find the limit of hx as x tends to 0. As x tends to 0, the limit is negative 1. The limit is negative 1. And we have to multiply it with the limit of f as x tends to 0. As x tends to 0 is something called 1.5, but that doesn't exist. Negative 1. Next, if x tends to 0 here, we have 1.5. Oh, basically f minus 1. F minus 1. So f minus 1 is bounded. So the limit doesn't exist. So what we do is we plug in. We find the limit of hx as x tends to 0, which is minus 1, and then we find the value of f minus 1. So as we can see, f minus 1x doesn't have a value. It is like infinity or undefined. So that's why we can't say there is a specific limit. Okay, we have to find the limit as x tends to infinity for this function. Okay, in the numerator, what we have we have x to the power 4. The denominator, we have x to the power cube. So as x tends to infinity, what will happen is it will increase more than this will increase, and ultimately this function will become unbounded because numerator is increasing more as compared to denominator, x to the power 4. The function f is defined over the real numbers. This table gives a few values of f. What is the reasonable estimate for the limit of this function as x tends to 5? So where is 5? It's here. It is approaching from both sides. Yep, it is. At a non-constant interval? Yes. And is it approaching of the same value from both sides? Yes, it is, which is negative 5. So a reasonable estimate would be negative 5. Next question. Gx is this function where x is not equal to 0. G is continuous for all the numbers. Find the value of g is 0. So if you plug in g is 0 here, it's 0, and it's also 0, and it's also 0. So 0 divide by 0. Indeterminable form. What do? We factor it out. So we can take x common from here. So we have x common, x squared plus 5 and 10x. So x cubed plus 5x is the same as this when you multiply. You can now cross out the x. Now you can plug in 0. So we get 10 upon 0 squared is 0 plus 5. So 10 upon 5 or 2. So what do you get? You get 2. Okay. Campbell's teacher gave her a flowchart below and asked her to find the limit of hx as x tends to negative pi by 4 for this function. So obviously the very first approach is Trig substitution. You have this equation that they have given. Try and plug this one a as minus 4. So negative pi by 4. It's 0. It is 0. So now we have to see which one is 0, the denominator or the numerator. So we're told to find this function as x tends to negative pi by 4. So we plug in, multiply it with negative pi by 4, 0. What about this? If you plug in negative pi by 4. Okay, so basically this is also 0. It's a very extremely small value. So 0 upon 0 is basically indeterminate from D. Okay, indeterminate from, this is 0, almost 0, because it's a very small value. What do we do now? It's a trigonometric function. We use trigonometric identities, G. What trigonometry identity can we use? We can write cos 2x to be cos square x minus sine square x divided by cos x plus sine x. And we know that a square minus b square equals to a plus b minus b. So cos x plus sine x divided by, cos x plus sine x. A square minus b square equals to a square, a plus b into a minus b, cos x minus sine x. We can cancel this out. We are left with cos x minus sine x. Now we can apply the Trig substitution again. So Trig substitution, because we have cos x minus sine x. So cos x minus sine x to get a value of 1.4. So yes, Trig substitution, limit found. Okay. So gx equals to 1 upon tan x squared. Select the correct description of the one-sided limit of gx at x equals to 0. Okay, so 1 upon tan x squared, this equation. What happens when we approach x equals to 0? As you can see, from negative side it's infinity, positive infinity, and from positive side is also infinity. So from both sides it is positive infinity. Okay, consider graph of the function g, which limit expressions agree with the graph. Okay, limit of this gx as x tends to -1, as x tends to -1, from the negative side is 6. As x tends to -1, from the negative side is not 6, it's 2. -1, -1, negative, so the negative side is 6. It's not true. Limit of this graph as x tends to 4 is 5. As x tends to 4 is 5 only from one side, not from both sides, so we can't say this is true. X tends to 6 is -1. As x tends to 6 is it's 4. It's not true either. None of the above, because graph of this as x tends to 6 is not -1. This is okay, x tends to 6 is 4, but they say -1. No, it's not true. Okay, what about this? Sine 2x divided by cos 2x. Sine 2x divided by cos 2x. Okay. So you have to plug in pi by 2. It's 0. What about this? It's -1. So cos x is -1. We have to find the limit of sine 2x divided by cos x, not cos 2x. So basically, yeah, 0 divided by 0. This is indeterminable form. Sine 2x is 0 and 0. Okay. What do? We use trigonometric identities. Sine 2x can be written as 2 sine x cos x upon cos x. So we are left with 2 sine x. So basically 2 into sine x, which is 2. So our limit is 2. Okay. Let gx be equals to this function for x is less than equals to 1, and this function for x is greater than -1. Is g continuous at x equals to -1? Well, let's plug in e to the power x. If you plug in -1, we get a value. We should get the same value for negative. Okay. So -1, negative becomes +1. Negative e to the power +1 is not the same as e to the power -1, as you can see. So is this continuous? No. The function is defined for all real numbers except for x equals to -4. As you can see, it has a removable discontinuity. What is a reasonable estimate for limit of this, function as x tends to -4? As x tends to -4 is from the both sides. As you can see, it approaches something like number 5, and it is greater than 5, so it's -5.2. Not any of these. Consider the graph of the function h. The dashed line represents asymptotes. Find the limit of h at limits of h at negative and positive infinity. What happens when x tends to negative infinity? You go on negative infinity, you reach the value -1. You keep on going to positive infinity, you reach the value 5. Limit of this function as x tends to -3. So we have 4x squared plus 12x x squared plus 4x plus 3. X squared plus 12x, x squared plus 4x plus 3. We have to find, let's define this as, let's say this is h of x. If you plug in -3 here, we don't get any value. So we have to factor this out. This equation here, we can write it as x plus 3 and x plus 1. It's the same as times as you can see, it's the same graph. So we can write the denominator like this: x plus 3, x plus 1. And what we can do is from here we can take out 4x common. So we're left with only 1x, and we are left with 3. Okay, 4x squared plus 4 3s are 12, 4 3s are 12x. X plus 3 can cancel out. We have 4x upon x plus 1. So 4x upon x plus 1 is almost the same graph, as you can see, except for x equals to minus 3. So here x equals to minus 3 has a value, which is -6, but this graph here does not have a value. Like undeterminable form. So 4x has a value of 6. If you plug in -3 here, six. So this is our answer. 2 to go. The function h is defined over real numbers except at x equals to 6. This table gives select values of h. What is the reasonable estimate for the function as x tends to 6 from the negative side? So you have 6 here from the negative side. So it's 5.995, and from positive side is 6.005. We want from the negative side. So negative side is approaching to -6. As you can see, it's getting closer and closer to -6. So we can say that it is -6. Last question. hx equals to this function for x is less than -2. So this is the 0, this is -2 for less than this function, for less than this interval, and between -2 and 1, so this interval. It is this function. What is the limit of hx as x tends to -3? What is the limit of this function as x tends to -3? Where does it fall when, when we go to -3? This interval. So with this function. So if you plug in 2 into -3 plus 1, we get -6 plus 1, which is -5. And that's it. That marks the end for this unit test.